Hi everyone, welcome to my talk. My name is Ana Margarita Medina. I'm a chaos engineer at Gremlin. I've been writing code since 2010, and I got a chance to start working in production systems in 2016 when I became a site reliability engineer. I also got a chance to get started in chaos engineering in 2016 when I joined Uber. I've gotten a chance to put a lot of my passions together, and I joined Gremlin 2 years ago. Some other non-work related fun facts about me is that I love traveling. I'm a huge advocate for mental health and diversity in tech. I'm also a proud Latina. I was born and raised in Costa Rica and my parents are Nicaragua. I now live in San Francisco, California. Today's talk is about using chaos engineering to build resilient cloud-native applications with Redis. Thank you all for coming to my talk, but for those that came to my talk and are wondering why should I think about building more resilient applications? My applications are already pretty fine. Well, we start seeing that our systems are getting more distributed. They're getting more complex. Many folks are moving from bare metal data centers to the cloud, and they're not necessarily know how to operate these things with high uptimes and lots of nines of reliability. We can see that complexity keeps increasing. There's various reasons for this. We see folks moving from monoliths to microservices. This is great because it increases developer productivity. There's more ability to scale, but some of the bad parts of this is that there's thousands of microservices, as you can see here on this Death Stars. And this just leads to us needing more ways to actually test the way that we build our systems. We also see a lot of folks moving from bare metal to the cloud. Some of the great things with that is that it's a decreased cost, it's low maintenance, and we have better ability to scale. But the bad on that part is that we have less control. So we have to think about ways that our applications are degrading in a safe manner, but also continuing to be reliable for our users. These Death Stars are from 2015. Imagine how more complex the systems of Amazon.com and Netflix are now in 2010. If you only remember one thing from my talk, I want you to remember that failures are inherent to complex systems, and this will cause downtime unless tested for. We always assume that our systems are going to handle many of our failures in a pretty okay fashion until we get paged for that incident, until our users are not able to have a good customer experience. So let's actually go ahead and test for those conditions. Failures are everywhere. You actually might feel like this image very often. I keep getting paged. This is fine. All my other coworkers continue getting paged. And well, there's a world where our pager fatigue can be a lot less. We can be woken up a lot less during the night. And we can make sure that our systems are continuing to run without us needing to be there fixing them so often. Failures are happening everywhere. Choose a technology that you like. Put it on Google. Put outages. Choose any date. You can see that there's a huge community of actually talking about our failures so we can actually continue learning from them as a community and build better systems. And reliability matters now more than ever. In current times that have us at home, that means that more users are actually using our applications. Have we actually tested for that extra load? But also, some cascading failures can actually happen through this entire process that we're all going through. We're having so many new engineers that have never been working on our systems or running production that are now keeping those systems up to date. Are we actually training them in a good fashion? Are we making sure that things are scaling reliably? Are we keeping our runbooks up to date? So in my talks, I usually like asking folks, have you heard of chaos engineering? But since you're watching from home, feel free to tweet me at Anna_M_Medina if this is the first time you've heard about chaos engineering. You can also use the hashtag chaos engineering hashtag on Twitter and tell us about some cool stuff that you've learned from today's talk or as you do more research in this topic. But for those that have never heard of chaos engineering, what is chaos engineering? Chaos engineering is thoughtful, planned experiments designed to reveal the weakness in our systems. Chaos engineering is not about breaking things on purpose. Chaos engineering is not about bringing down production. There's an entire method on how you actually do chaos engineering, and we'll reference that very shortly. But I want you to remember that this is thoughtful and planned. So you actually want to think about how you want to execute your chaos engineer experiments, but you also want to communicate with other folks around you that you're running chaos engineering experiments. And don't forget, the reason that you're doing such experiments is that you want to make your systems more reliable. So how do you actually go about performing chaos engineering experiments? Well, first, you start by observing your system. This can mean that you can actually just pull up an architecture diagram and see how your application behaves. Then you actually want to have some baseline level metrics of your systems. This can actually be done by setting up some SLOs, some SLIs for your service level objectives, and service level indicators. Then you want to go ahead and form a hypothesis of your chaos engineer experiments. But don't forget, when you create that hypothesis, also think about what are some conditions that would cause me to halt this experiment. If my users are being affected, is one of our examples, response time being down, and anything that impacts your SLOs or SLIs. Then you want to go ahead and define the blast radius. This is about doing chaos engineering in a thoughtful manner, and you want to start off with a small blast radius. That might mean that you actually start running chaos engineer experiments in staging, dev, QA, prior to moving on to production. But one of the other ways that you can actually define your blast radius is by the amount of hosts or container or applications that you're targeting in your chaos engineer experiments. So don't go ahead and run your first chaos engineer experiment on all of your fleet if you actually don't know how this chaos engineering experiment behaves on just one node of your system. Then you want to go ahead and run your experiment. Make sure to keep your abort conditions in mind and have some monitoring observability in place that you can actually see how things are being affected. Then you want to analyze those results. Is this chaos engineering experiment successful based on your hypothesis? If yes, go ahead and expand that scope and retest it. If the experiment wasn't successful based on your criteria, go ahead and make your systems more reliable and then go run that experiment one more time. And one of the other things that we ask for folks to do with chaos engineering is share your results. Share about some of the learnings that you have by doing chaos engineering experiments so you can make not only the chaos engineering community, but a lot of the open source communities that a lot of folks are using. So how can you actually implement chaos engineering on Redis? Some questions that you can actually start off when you're doing chaos engineering on Redis is ask yourself, did I set up monitoring for Redis properly? Are my runbooks to operate Redis up to date? There's nothing worse than opening up a runbook and seeing that it's 200 days old when you're currently getting paged for an incident around Redis. Another one is when Redis suffers some latency. What happens to your upstream dependencies? How about your downstream dependencies? What are the timeouts on your APIs or other services that are actually pulling in information from Redis? Another question to ask yourself, is your Redis configuration set up to perform a region failover? These are some questions that we might actually think that our systems are able to answer all these questions in a pretty okay manner. My monitoring is set up, but I won't ever know unless I get paged for it. So with chaos engineering, we can actually answer some of those questions for ourselves on our systems. So I'm going to do a little bit of a demo of some chaos engineering experiments that you can do on Redis. My first experiment is I'm going to grab the PHP guestbook application with Redis from the Kubernetes tutorials. The way that Redis is set up for this tutorial is that it's a single instance of Redis master to store the guestbook entries. Then there's multiple replicated Redis instances to serve reads. And we also have some multiple web frontend instances. Let's actually see how this all works together. The chaos engineering experiment we're going to do is we're going to shut down the primary Redis container since we have replicas that are in the back. We're going to be targeting just that Redis container. The failure is going to happen for just about 60 seconds. Some of the abort conditions for this experiment is that if I start seeing HTTP 400 errors, 500 errors, we start seeing issues on the front end, or we actually suffer a data loss, we're going to go ahead and halt that experiment. My hypothesis is that by me shutting down my primary Redis container, I believe my replica Redis containers are actually going to get promoted to primary, and my application would continue working successfully. So let's go ahead and mark no impact on our hypothesis. We're going to go on here, and I'm just going to show you how this has been set up. We'll do kubectl get nodes. We have 3 nodes running in the back. We'll do kubectl get pods, all namespaces, and we see we had Datadog deployed. We have 2 front ends, a Redis master, 2 Redis replicas. Gremlin has been deployed, and some stuff on the kube system as well. We're going to go over to K9s just so we can see a little bit more information of things. Let's hit up the front end, and let's actually do what a user would do when they're using this guestbook. I'll type in my name. I'll also check in my middle name. We'll also leave one more message. Carol says hi. And one more message. Maria dropped by to say hola. Cool. I've been able to put 4 entries. My application's running pretty successfully. So let's go find out some more information into how this Redis has been set up. We'll pop over to bash Redis CLI, and we'll do info on replication. We see that we have 1 master and 2 replicas. Cool. So my hypothesis is going to be that as I shut down my primary, my replicas are going to get promoted and there won't be any data loss. So we're going to go ahead and actually run that experiment. I've made the API curl. Now let's actually go test our guestbook. We see that all of our entries are on there. I'm just going to try that out. Uh-oh. That's actually completely showing a data loss. This is definitely not the best experience for running experiments like this. And this actually means that my hypothesis is wrong. If we were to suffer a data loss, we should actually go ahead and halt that experiment. Maybe at this point, restore from a backup just to make sure that we continue keeping our systems up to date. But the reason that this failed the way that it did, and we actually see Redis having a data loss, is that the example of that Kubernetes gives us on how to actually deploy Redis on Kubernetes is actually not an industry best practice. As you can see, there's only 1 master, and the replicas are only serving as reads. So definitely, if you're trying to set up Redis, do some more research on better ways to deploy Redis into your Kubernetes environments. This is definitely not the best way. But this actually shows us that a lot of the tutorials that we do use as industry best practices, they're not reliable from the start. And that's actually one of the things that chaos engineering can help us uncover. Prior to us going and implementing an entire new open source tool or tooling into your systems, let's actually go ahead and test the configurations early, just to make sure that as we deploy them into our systems, they're reliable from the start. So just to recap this first experiment, I wrote in the results. Our hypothesis was wrong, and this impact was large. Imagine having a full-on data loss on your production systems. This is not good. So we're actually going to put a conclusion that we want to go ahead and dig deeper and find out what is the ways that we could actually grab this setup and just make it a little bit more reliable. One of the ways that you actually deploy Redis in a very different way using one of the many Redis operators that are available for Kubernetes. But you can also use that same configuration and set up some extra layers of reliability, such as setting up Sentinel for Redis. Moving on to our second experiment, we're going to switch over to a microservice-based demo. We're going to use the hipster shop that Google Cloud has open source. And this is a 10-tier microservice demo application. The way that Redis is actually being used in this application is that it's going to be used as a cache for anything that we add to the cart. Just to give a little bit more of the architecture diagram of this 10 microservices is that we have a load balancer that is being connected to the internet. This actually shows our front end. The front end is actually calling the cart service, the recommendation service, the product catalog service, the currency service, checkout service, and ad service. All these microservices are on the critical path of our application. And we can see that in the cart service, that's actually calling Redis to be the cache layer. So for this experiment, what I want to do is that I actually want to inject 100 milliseconds of latency into our Redis container just to actually see how our application handles slow response times from Redis or other applications that are being used to pull information from that cache. This experiment's also going to last 60 seconds. My hypothesis is that my hipster shop is actually going to have a degraded performance. But as I mentioned, we want to have some abort conditions that would cause us to actually halt this experiment. Some of the abort conditions that I have for this experiment is that if I start seeing some HTTP errors of 400 and 500s, I want to go ahead and halt that experiment. Then once again, if we suffer any data loss on anything we already have saved on the cart, let's go ahead and halt that experiment. And then I'm also going to put an abort condition if our response time for our hipster shop goes above 500 milliseconds. I'm going to go in and halt that experiment as well. So let's actually go see if our application has a degraded performance. We actually get to show you a little bit of the steady state of this hipster shop. I'm able to browse around, add things to my cart. I've added 2 items and then I can go and place my order. This is a steady state. In just a few seconds, I'm actually able to add things to my cart and check out. But let's actually see how long it's taken for all these requests to be put. 62 milliseconds, then followed by 74 milliseconds. We see 75 milliseconds for pulling up just a home page, adding things to cart. It's pretty fast, but these is what we actually get to categorize as some baseline level metrics for our experiments. We see that our cart has 2 items. And just to actually see how this application has been set up, since it's different than the one I just showed, we'll do kubectl get nodes. This is actually running on an EKS cluster on AWS. And when we do kubectl get pods all namespaces, we see the 10 microservices along with Gremlin and some stuff on the kube system for AWS side. We're actually going to target Redis cart. Whoopsie, did not mean to paste that there. Let's go ahead and run that experiment. And let's actually put a countdown for those 60 seconds, just so that we can see how this experiment is going for the length of the experiment. We added that to cart. We start seeing that those response times are going up actually almost by 100 milliseconds each. That's 246 milliseconds, 172, 311. This is still all under the response time of 500 milliseconds as I had as an abort condition. So this is actually really great. Our experiment is still running. Our systems are up and running. We haven't hit any abort conditions. This is the ideal view of running some of the chaos engineering experiments on your system. You have come up with a hypothesis based on some baseline level metrics. You run it, you're able to execute on it, see that your system's able to withstand such failures. We add things to cart, things are still working. And our experiment's going to be ending soon, so let's actually see how long it takes for your systems to come back into steady state. We still see the response time was high. Okay, we're down to the response times being less than 100 milliseconds. That's back to steady state. So our application was actually able to withstand those 100 milliseconds of latency we threw into the Redis cart. So that means that the conclusion for this experiment is that it was actually expected. We expected a little bit of degraded performance. Those extra 100 milliseconds of latency didn't affect our use cases that we were trying to use onto the application. Things were able to actually still load, add to cart without any error codes, without hitting any data loss, and with response time still being less than 500 milliseconds per request. So the result of this experiment is that our application was able to handle 100 milliseconds of latency quite well. So let's actually go ahead and automate that experiment. I've actually ticked it off on the conclusion side. And one of the other things that we can actually do is that we can increase the magnitude of this experiment so that we can actually test how our application behaves when we actually throw just 200 milliseconds of latency and later increase that magnitude once again to 300 milliseconds of latency. This can actually help us make sure that all the Redis requests that are all the API requests that are coming into our Redis are actually hitting the right thresholds that we want it to. So for the third experiment, we're going to expand a little bit on that blast radius that we had just done in experiment number 2. Instead of injecting more latency, we're actually just going to stop serving traffic from Redis. Since it's the cache, we actually think our application will work pretty okay. We're just going to have a little bit of degraded performance. Maybe we'll actually just see a little bit of latency on our side. So for abort conditions, we're going to put the same abort conditions of 400, 500 error codes. We're also going to put an abort condition around data loss on anything we currently have on the cart. So let's go ahead and see how this experiment runs. We see that we're able to browse things, place orders. And let's go back to K9s just so I can see all of our application. We'll go down to our Redis cart. We'll bash in. We'll pop over the Redis CLI and just browse all keys. I'm just curious on how Redis is actually being used. So this is actually, I believe, how all the items are being stored into the Redis. So all the data is on there. Our application is still working. Just had to make sure one more time. Now let's actually go ahead and run that black hole experiment into our Redis cart. We'll go ahead and actually put a countdown again, 60 seconds. And let's go try to browse that page. We're starting to see that the requests are actually not going through. And this is definitely taking more than those 5 seconds that we would expect and that we have as an abort condition. So let's give this one more try. Uh-oh, 500 internal server error. Could not retrieve cart. And this actually has a full stack trace of our entire call. Yeah, let's actually go ahead and abort that condition. I've gone ahead and halted my experiment, but I also just want to put a countdown just to see how long it takes for our systems to come back up. So black hole should have, the rollback should have actually kicked in by now, but our application actually might be suffering some cascading failures from this experiment. It's actually taking a bit for our Redis cart to actually start coming back and getting connected back to our application. So this is definitely not ideal. This is also that part where we're able to see that an entire stack trace being shown on an error page is also not good user experience. We definitely don't want our users to be seeing any of these error codes. We want to handle them in a better fashion, but we also have to think that the stack traces can actually have some critical information that users should not be seeing as well. So let's make sure to file a ticket for this issue as well. We see that it's been over 60 seconds since the experiment has halted and our systems are not back to steady state, which this is definitely not a good experience. We want our systems to come back as quick as possible and just kind of like bounce back and be resilient for issues like this. This is still at 1:24. And our application's back. Let's actually go test this compared to steady state. We add something to our cart. Okay, so that worked. So it took about 1:42 for our systems to come back up after we've run our experiment. This is definitely not ideal, and this is some stuff that we actually want to write in our notes. This was an ugly 500 error page with the stack trace, and experiment took a while to come back into steady state. So we actually want to put a conclusion to dig deeper. Just to recap some of the takeaways that we actually have from our experiments is that we want to test the resilience and durability of Redis early and often. As you implement Redis into your applications, into your organizations, make sure to do some region failovers, test latency, black hole traffic, make sure that your application is able to happen when some timeouts are going on. You also want to remember that our applications should gracefully degrade whenever possible. And one of the other takeaways that we can have from this experiment is that we want to be creating experiments based on common failures. I mentioned that performing chaos engineering experiments is also about sharing the results, so we make sure that our colleagues are able to learn from these failures. So we can actually go ahead and look into the outage communities, the postmortem communities, and see some of the common failures other folks have had in their organizations as they have made their Redis implementations more resilient. We can actually learn from them and run chaos engineering experiments based on the conditions that they have talked about that have caused failures in their systems. So to recap how you can actually go ahead and practice chaos engineering, well, as I just mentioned, you want to create applications and systems that gracefully degrade. You also want to go ahead and train engineers to be on call. Usually when we ask folks how they got trained to be on call, it's usually they got thrown a pager at them and got told, hey, you're on call. Or nowadays you just get given a PagerDuty account. You also want to go ahead and learn from others' failures. There's a full community of folks that are actually talking about their failures openly in their systems and in their organizations. So with that, you want to regularly exercise past failures to not drift into failure. If you know that you've actually been able to run some chaos engineering experiments successfully, go ahead and actually automate them so that you're not regressing into some of the issues your systems have had before. And lastly, don't wait to see how your systems handle failure. Be proactive and inject those failures as often. If you're interested in learning more about how Redis works with Gremlin, you can check out this webinar that's happening on May 20, led up by Gremlin's principal SRE, Tammy Butel, as well as David Henderson, a solution architect at Redis Labs. So make sure to tune in, and to get more information on that, you can go over to gremlin.com/Redis. And there's a full community of chaos engineering out there. If you're interested in getting connected with the chaos engineering community, go over to gremlin.com/Slack. You'll find a lot of resources and tutorials on there, but you'll find that there's a way to get an invite into the Slack community. And this has almost 5,000 engineers on there, from folks that have never run chaos engineering experiments to folks that have been doing chaos engineering for 5-6 years. So with that, I'd like to give you all a huge thank you for watching my talk. Thank you, RedisConf, for having me as a speaker. If you would like to follow up on my talk or have any more questions around chaos engineering, feel free to email me at anna@gremlin.com. You can also find me on Twitter at Anna_M_Medina. And if you're interested in giving Gremlin a try, head on over to gremlin.com/RedisConf 2020, and you'll get a chance to sign up for our Gremlin Free Forever account. Thank you.